see. I got enough memory.
All right, are we ready to go?
There we go. Yep, we are live.
Okay, everybody, thank you for joining us today. Uh, as usual, today we have our yearly visit with Agapios. Um, it's an absolute honor to welcome our guest speaker, Agapios Elia. He's a passionate and accomplished expert in planetary imaging, as well as deep sky and all other forms of imaging. He's got a deep fascination of the cosmos and years of dedication capturing the beauty of our solar system. He's just so blessed to have the wonderful conditions that now have just gotten better with this enormous telescope. Agapios has developed this reputation for blending scientific precision with artistic mastery in his work. As a skilled planetary imager, he is not only contributed to the study and understanding of celestial objects, but have inspired countless individuals to look up at the night sky with awe and curiosity. I know many of us have gotten inspiration from Agapios. Um, Through his expertise, he transforms distant worlds, planets, moons into stunning visual masterpieces, making the mysteries of space more accessible to us. So today, Agapios will guide us through the fascinating field of planetary imaging, sharing his insights, techniques, and challenges, and wonders of capturing the breathtaking beauty of our neighboring worlds. Please join me in giving Agapios a warm welcome.
Wow, now that was some introduction. Thank you so much for that, Lou. The honor is all mine. Thank you so much for the opportunity. As you know, I greatly enjoy sharing what I get to do, what I'm blessed enough to be able to do. I greatly enjoy sharing it. And tonight is a special night because I'm joined by a new rising star in the field of astronomy, at least here in Cyprus. Chris, who's with us on the call, is my assistant for the night and for many other nights. A rising star in astronomy. He's become really proficient in using telescopes, exploring astrophotography on his own. And there's a bright future ahead of him for sure. And I'd like to say thanks, Chris, for coming up and helping me with the big beast that we're going to be using tonight. And we've got a nice show, I think, worked up for you guys tonight. We had a bit of a scare because the weather today wasn't exactly what we expected, but thankfully, just a few minutes before we went on the call, the clouds parted. It's a beautiful, crystal clear night above us, and it looks like the seeing is cooperating. It looks really good on the live feed that I'm showing now, but I'm not going to show you just yet, because what we would like to do is give you a little bit of perspective. Now, as you know, we're in Cyprus, and Chris now I think you can share, and he's going to show you where exactly we are. Let's see if we can get this right. There we go. So that's where you guys are, somewhere there. So across the other side of the planet, at the eastern edge of the Mediterranean Sea, there we are, is the beautiful island of Cyprus. Now, the island is tiny by all comparison, just 220 something kilometers across, and we are smack in the middle of it, just below the summit of Mount Olympus, which is the highest mountain on the island. That's about 6-something thousand feet. But we are at 4.5 something thousand feet near the village of Agridia at the National Observatory. Now, if you remember, we did a sort of an impromptu tour at the beginning of the summer where I walked you through the premises of the observatory and we got to see the telescope and everything. This is our first observatory as a nation, our first proper observatory. It's been a long time coming, and I'm very happy to say that we are finally here, and we are just about ready to start accepting visitors. We're going through the process of commissioning everything, making sure everything is up to standard, and to be able to give a high quality experience to the students, to the visitors, to amateur astronomers, and to tourists. Why not? So when you all decide to come down, you know where you're going to stop by. So the observatory is at 1,250 meters above sea level. That's 4.5 something thousand feet. And we are at the eastern side of the Troodos mountain range. And out of all the nights that I've managed to be up here, ever since we installed the telescope, it's looking like it's proving to be quite a good location. I mean, definitely the altitude helps a lot, but it looks like the seeing here is often very good, as is the case tonight. So I don't know if Chris, can we show the building? Is it on Google? Let's see if we have any pictures on Google. There we are. So the building is really unique. It's almost like a spaceship that's landed on the mountain. That's where we are right now. And we've got two telescopes in the observatory. One is our dedicated solar scope that's under a roll-off roof. You can't really see that on the screen now. And the main telescope is our beautiful plane wave 20-inch CDK reflector. That's on a Paramount ME2 heavy-duty mount, and it's got foundations, really heavy-duty foundations, able to support much larger telescopes. But we're going to start small and work our way up. The telescope is under a what's in feet? 6 meters, 18-foot dome. So we've got a big 18-foot dome here that's ASCOM compatible, so it talks to the telescope, and we're able to synchronize the two. Yeah, we're ready. We've got a beautiful night sky, and tonight we're going to be talking about planetary imaging, which is the craft or art of capturing images of solar system objects, namely the planets. We're coming up on the opposition of Jupiter, where Jupiter is ideally placed in the sky. And not only is it ideally placed, meaning it's visible for a large period of the night, it's also at its closest to the Earth. So it appears the largest it can appear through a telescope. Typically, Jupiter grows to about 50 arc seconds across. That's probably the most that we've ever been able to get Jupiter. So it's the largest of the planets. It's the most vibrant, the most dynamic, the most complicated in terms of its workings, its atmosphere, the way things work on Jupiter. And because of the Galilean moons, it's also very interesting to observe because there's all kinds of stuff happening all the time. So I'm going to steal the screen now, and I'm going to share mine. Okay, there we go. And let me know if you can see fire capture, guys.
Yes, we see it.
Yeah.
Let's see. Okay. And here's where I'm going to be needing Chris, because we've discovered the bad thing about using big telescopes, which is that they're big, really big, massive. So anything you want to do, you need to have somebody else to help you. So Chris is now targeting the telescope. You may want to check the finder. So Chris is now going to be targeting the telescope and using the focuser. We haven't exactly fine-tuned everything to be able to control everything from a single point. We're in the process of doing that. But for now, we've got Chris. So We're going to torture Chris tonight a little bit. He's going to get us on Jupiter. We haven't yet been able to perfectly polar align as well, but we should be almost there. Well, we saw a moon before. Let me just maximize the screen here. Bear with us, guys. No? Yes. Not yet. See, something is zoomed past the screen. Again, something is zoomed past the screen. You wanna be able to see? So as I said, the bad thing about using big telescopes is that you need to have somebody helping you, and I can only imagine what it must have been like 100 years ago when astronomers were using telescopes like the 100-inch or the 200-inch. I don't know what's it called, a Hale telescope, where you have to have an operator and you have to shout to him, "Yo, move the telescope this way, move the telescope that way." You want me to try?
I think the dome might be in a little bit of money.
Yeah, you want to turn the dome a bit?
Yeah.
Okay. So while we get that going, no, you see, parallax got in the way, and you should be on it. No, that's fine. It's fine.
There you go.
There we go. So that's one of the moons, and there is Jupiter. Okay, back in business. This is what happens with the live shows. So there's Jupiter. So a little bit about the equipment. As I said, we're using a 20-inch plane wave CDK telescope. The focal length on this telescope, the native focal length, is something like 3,500 millimeters, and that works up to about f6.8. So it's not what you would typically use for high resolution planetary imaging. This is more of an all-purpose telescope, but it has proven to be very capable. I mean, the initial test shots that we were able to take a few weeks ago were very promising. And we're still waiting for our primary camera. So we're using my personal camera tonight, which is a Player One Saturn C. That's the IMX 533 based camera, a color sensor, 3.75 micron pixels, and 3000 by 3000 pixel sensor size. And it's at least for me, it's proven to be a very, very capable camera. And we've also got an atmospheric dispersion corrector, a filter wheel, and a ×2 Barlow lens. So the telescope is now working at roughly f13, at roughly 6,000, 7,000 millimeters of focal length. Now, as you can see, we are now looking at the live image, and we are also using the entire sensor. So this is how big Jupiter appears on a 3 by 3000 pixel sensor. It's still small, but thankfully we've got the ability to zoom in a way. We can crop the sensor so we can get rid of all of the dead black space and just focus on our target. And if you have a mount that is A, really well polar aligned, and B, able to track adequately, if you've got a really good polar alignment, you can crop in really tightly and use a very small box, a very small region of interest, And what that will get you is a much improved speed in capturing, which is really, really important, especially if you don't live in an exotic location or you don't have your own observatory. So what we're going to do now is I would like for you to just concentrate here. We're using the entire sensor and we're doing approximately 40 frames per second. So every passing second, the camera is able to capture 40, 42 individual frames. What we want to do is we want to maximize that number to combat the variability of the atmosphere. So the first thing I'm going to do is I'm going to bring my planet to the center. I'm using a little joystick here. There we go. And I'm also going to click and drag a tight box around the planet. Click OK, and I'm going to zoom in to 100%. There we go. So you'll immediately notice that the FPS has shot up to 130. That's much, much better, much more desirable for the kind of imaging that we want to do. And if we can get the focus going, and Chris, can we also turn off the fans on the telescope? So we've got our focuser here. I'm going to try and see what we've got going on. So from what I can see, the seeing has gone down only a little bit. It was slightly better before. There we go. This is good. And let's recenter. Yeah, that was Chris attaching the focuser back onto the telescope. Okay, here we are. Now, what I'm going to do is I'm going to record 60 seconds worth of video at 130 frames per second. So that's going to give us a good number of individual pictures, which we will then process to combine and stack them so we can sharpen them and extract the maximum resolution that we can from the telescope, the camera, and the conditions. So guys, feel free to jump in at any time. Planetary imaging, we were talking about it on the way up. Planetary imaging is much more lively, much more interactive, and much more immediate than your typical deep sky imaging session where you shoot the same target for many nights or for a long period of time. We're dealing with exposures that are a fraction of a second, and we're shooting at most a period of about, I don't typically do more than a couple of hours of total capturing time on a planet. So it's a much more immediate experience, a much more interactive experience, and we can do this in a way, in a form of a joint session, of a workshop. So feel free to jump in with any questions or comments that you may have.
Agapios,
I am known to go on and on. Yeah, go ahead.
quick question.
Yeah, hi, Steve.
What's your focusing technique?
Okay, so to put it simply, staring at the screen until things look right.
Okay.
To give you more detail, there's definitely a place for having a quality focuser. Now, this telescope has a really high quality focuser, which is computerized and motorized, and it comes with a hand controller and software, so I can really focus with high precision. But even if you don't have access to that kind of equipment, even if you have a more, not rudimentary, more common household equipment, fire capture has a really powerful tool that can help you focus with extreme precision. What you have to remember is you're using such a high focal length, such a high magnification for this kind of imaging that you're really zoomed in to the extremes. So any slight movement, any slight adjustment on the telescope will result in massive shakiness, to put it simply. Now, fire capture has a really clever tool called auto align, which basically lines up the incoming frames from the camera on the fly so that it looks like the image is frozen on the screen, and the telescope becomes unaffected to your touching and leaning and squeezing and adjusting. So I'm going to demonstrate that now. We don't have auto align turned on yet, and I'm just going to wiggle the cable. See how Jupiter is wiggling? So this is what would happen if you were to touch a focuser on a telescope and attempt to focus. But what I'm going to do now is I'm going to turn on auto align, which is here. And you'll notice immediately that the planet is centered and it's not moving up, down, left, and right. It's shimmering because of the atmosphere. But I'm going to wiggle the cable now. See that? No movement whatsoever. This helps greatly when you're trying to focus your telescope and you're touching it. So I highly recommend that you consider using this tool. It's going to make things night and day for you. I know a lot of people like to use auto align when they're recording, but there really is no benefit to recording with auto align turned on. There's actually a drawback. It's costing you capture speed. So you don't need to have it on when you're actually recording. You can turn it on to adjust things, and then you can turn it off again. Another thing, when it comes to planetary imaging, you're really at the mercy of the atmospheric conditions, and these can be highly, highly volatile, highly variable. In our case, on the island of Cyprus, what typically happens is predictions come true for a fraction of the night. So if the prediction is for sub-arc second seeing and excellent seeing, that usually materializes for a fraction of the night, and nobody knows when that would happen. So I've talked about this a lot. I've done a lot of presentations about it. I've sort of developed a method. I shouldn't say developed. I should say I've stuck to using a particular method of shooting continuous files over extended periods of time, typically around the 1 to 2 hour period. So what I'm doing is I'm continuously shooting. There's another tool here in Fire Capture called Auto Run. Let's see. Right here, the running man, where it allows you to shoot consecutive files with the exact same settings. So I'm going to turn that on now. I'm going to ask it to do 10 continuous 1 minute long videos. And tonight, actually, the night is actually really good, quite steady. So there's not going to be much variability between these consecutive files, but I have seen extreme variability between consecutive 1 minute captures many times, where back to back you have extremely poor seeing to extremely good seeing within the span of 2 minutes. So there is just no way that you can be that lucky all the time and hit excellent seeing anytime you want to image. It's more the case of getting out there and shooting for large periods of time and hoping that the improved conditions are going to land somewhere within your window. And by using this method, you are sort of fishing with a net instead of a line. So if it passes your way, you're going to catch it. There's no way you're going to miss it.
Hey, Agapios,
Yeah, go ahead.
I noticed that when you're collecting the data, it's in mono, and when you're just looking at it, it's in color. Can you explain what's going on there?
Of course, excellent observation. That has to do with capture speed. So when you're capturing, you don't need to capture the color information because we have software that can remap the color information on your image. So capturing in full color will cost you more data, and more data means less speed during capturing and larger file sizes. So we use this process called debayering, where we ignore the color information coming from the sensor, and we just use the light information in total. And because we know the pattern of the Bayer matrix on the chip, we know exactly how the color filters are mapped on the chip. We can translate that in post-processing so that we don't need to have the actual color information at capture. So it's sort of remapping the color at a later stage. If you don't mind shooting multitudes of gigabytes per file, then and you've got a monstrous computer to process, then you can ignore this bit of advice. But if you've got something more mainstream, then highly recommended that you shoot Bayer data, so you don't have the color information. It all mostly has to do with the speed of capturing. And even if shooting a high frame rate means that the individual frames are noisier or appear to be noisier, what's going to happen is at the end of your capture, you're going to have more frames to stack, so your signal to noise ratio is still going to be very, very high. So we're shooting consecutive shots of Jupiter. We're looking at the so-called boring side of Jupiter, the side without the great red spot. And we can see the new disturbance that's been happening on the south equatorial belt. Jupiter has these two dark equatorial belts, the north and the south. And right about here is the new disturbance that's been going on for, I think it's been a couple of weeks. Originally spotted by, I think it was Christopher Go, who was the first to spot this new outbreak. It was either Christopher Go or Damien Peach who spotted it first. Those two guys are the absolute kings of planetary imaging. One is probably the most productive imager there is, Christopher Go in Philippines. He shoots every night or almost every night, so he's the most productive. Damien Peach is probably the most accomplished overall. The man is a wizard when it comes to doing what he's doing. So I highly recommend that you look up those two names if you want to do this kind of imaging, and you will learn a lot from the way they do things. So yeah, we've got the southern equatorial band, the southern equatorial disturbance coming up, and from what I can see, the seeing is looking a little bit worse. Now, what I would like to tell you about the seeing is that predicting the seeing is a dark art, really dark. Attempts have been made by many to understand it, explain it, predict it, and we've all failed miserably. The best advice I can give you is get out there and check with your telescope. That's the best way to know, because it's many a times it's been the case that I've happened to come up to really good conditions where I did not expect them. And of course, it's been the case many times that I was expecting excellent conditions, and I found really poor conditions. So it's really a dark art. But what you can do is you can make attempts to understand the local seeing where you live, how things work in your area, in your general area, how the weather patterns form, where the wind is coming from, and try to get out there as much as possible and actually take notes and see if conditions match predictions or not. And that will give you, at the end, after some time, you will have a really good understanding of how things work for you. That's what I've done for me. I spent quite a lot of time testing and attempting and just checking to see what predictions meant and what conditions actually materialized. And there is some correlation. You can get some idea of how things behave, but don't take any predicting website or resource or app very seriously. Don't just rely on that, because that's not a way to do things. I would say you can get a good indication from a website or from an app, but unless you're out there with your telescope and you follow the rules of the game when it comes to how you should have your telescope set up and tuned up, unless you're out there with your telescope, you never really know. The only way you can have predictable seeing conditions is if you happen to live at an exotic location, or a location that's ideal for astronomy. If you happen to live next door to an established astronomical observatory, or a tropical island, or something like that, where conditions are almost always good. We happen to live at such a place. We're very blessed to live here. Cyprus is, I call it the astronomer's paradise, because it's clear skies almost all of the time. And the seeing conditions can often be very good, very, very good, even excellent. You could move to Cyprus if you'd like. Happy to host you. And experience the beautiful night sky from here. So yeah, the best thing to do is just get out there as often as you can, but make sure you have done your homework when it comes to your telescope. Number one is collimation, which is the process of fine-tuning the optics of your telescope to make sure that it can see as well as it can possibly see. Oh, we're coming up to some really good seeing now. I hope you're enjoying the live feed, by the way. It's actually really good seeing right now. The process of collimation that has to do with the optics of your telescope is number one, because if your telescope is not perfectly collimated, then it doesn't really matter if you have perfect seeing, because you're not going to be able to harvest it. So number one is get your telescope as close to perfectly collimated as possible, and introduce the process of collimation to your everyday routine. It's not something that you've done once and you've done it well and it's done, and you check the box and it's done. It's something that you need to check and adjust every time you're going to be out with your telescope, every single time. And I'm very adamant about it, because when you consider that we're dealing with precision optics that have incredible amounts of resolution and we're peering through layers of the atmosphere, and we're looking at things that are so super magnified. Even the tiniest displacement of optics is going to have consequences. So you need to be perfectly collimated. And depending on what kind of telescope you have, there's methods, there's tools, there's software that you can use, and all kinds of aids into getting you well collimated. My personal preference is to use a bit of software called MetaGuide, which I've talked about many times. It is a software that visualizes collimation in a very clever way that points you in the right direction, both figuratively and literally, on to how to adjust the optics of your telescope to get near perfect collimation. And this is what we were able to do with this telescope the last time we were up here. Sorry. Which was a few weeks ago. We tried to collimate the telescope, this big telescope, using MetaGuide. And let me tell you, even if the procedure is fairly similar to a home-based Schmidt-Cassegrain telescope, even though the principle is similar, the actual experience was borderline scary, I would say. And the reason for that is the telescope is just so big physically that in order to get to reach the secondary mirror adjusting screws, I had to get up on a ladder. I was something like, I don't know what, 12, 15 feet up in the air, on top of the observing platform, which is about the height of a third floor where we are now. So I'm up there in the dark with my little headlamp, listening to Chris describing what's going on the screen, and we're just going back and forth, trying to get the telescope as near collimated as possible. But we managed to do a pretty good job, and from what we saw, from the data that we got the last time we were here. Oh yeah, can you share that? So Chris is going to share his screen now, show you a picture of what that looked like. Yeah, I've got this. Yes. So he's got a nice photo there. You sharing? Oh, there we go. So that's me, and I'm what you can't see is that I'm at about 15, 16 feet up in the air on top of the platform. There's the ladder over there, and I'm up there trying to do my best to collimate the telescope. So yeah, that was scary. I'm not looking forward to doing that again. I can tell you that. But yeah, we managed to get it as close as we could for the conditions. Yeah, and let's go back to the live feed. Yeah, you can stop. Yeah.
You do that. Do you have a monitor that's in front of you so that you know what you're doing, or you have to
You mean when I'm collimating up there?
Yeah.
No, I'm shouting to Chris and he's shouting at me. So he's describing what he's seeing on the screen, and I'm trying to understand and work out how to move things to get it right.
Wondering.
We did devise a plan that included multiple devices, screen sharing, mirroring, all kinds of things. But when it comes to game time, when you're up there on that ladder, you don't want to have to do many things. So we relied on good old shouting to each other to get it right. But it looks like we did, and by judging at the live feed, I think we did quite a good job. When conditions are superb, we can try again and get it even better, because I think we still have a bit of a way to go. But we've certainly been able to bring the telescope up to a very high standard, so that we can take advantage of the good conditions.
Well, look,
Yeah.
personally, I am terrified of heights as well. But
So am I, as I've discovered.
well, it might be worth it to get what do you call it? The uh, platform where you can set up so that you have a much more sturdier scaffolding. Uh, so you have a sturdier location, and then you can plop your monitor right there on the scaffolding and have a seat.
Yeah. Oh, there's many different things that we can do. I mean, the simplest thing we could do is, instead of using something up at the zenith, we could just use Polaris, or we could have just used Polaris, which is at a much lower angle. But we were obstructed by clouds that night, so we had to do what we could with whatever visibility we had. But we're not worried about that now, as it seems that the telescope is performing quite well.
Yeah.
And yeah, what we could do, if we don't have any more equipment questions, we can go into trying to process some of the data that we got tonight.
I have two questions.
Yeah, go
First is a suggestion. A taller ladder would be great. I always have the willies when the ladder ends at my knees.
yeah,
I'll have
yeah,
one
yeah.
hand on the ladder while you're doing something else with the other hand. It helps a lot.
We actually do have one, but it's stored somewhere where it's just not convenient right now to bring it up and put it up there. But we're definitely gonna go ahead and try and use something that's primarily safer
Yes.
than what we did last time.
Yes.
Yeah, for sure.
The question I had is about heat. Okay, heat is a big issue in telescopes when you're trying to get the best possible resolution. Is the observatory designed to minimize heat absorption and to deal with heat? And also, do you keep people out of the optical path so that their body heat isn't going up through the optics?
Excellent points all around. And yes, we've designed it with that in mind. In what way? First, the dome is insulated, so it keeps the brutal summer heat out. We get really hot summers here. And second, the observing room, the dome, is isolated from the rest of the building. So we can thermally isolate the environment here where we are. And there's also climate control in the room. So we can pre-cool the room to the ambient temperature of the observing time. So we can get things close to ambient quickly, and we can keep them that way efficiently. Now, as far as keeping people out of the optical path, that's not an issue because the eyepiece is at the back end of the telescope at eye level height, and the telescope is much higher up. So
Well, I really
yeah.
mean out from underneath the optical path. If body heat rises, of course, and if you create a heat plume and you're standing in
Yeah.
front, you know,
Yeah.
then you have to be, and that can hang around for a while.
What we do have in mind in getting is, well, we have disabled people in mind. There's a sort of an articulated extension that we can use to push the eyepiece away from the telescope, ideally closer to somebody who's on a wheelchair, and that would definitely help a lot because you're going to be something like 2-3 feet away from the telescope when we're looking at it. So that's one of the things that we have in mind in doing, and we're probably going to do that together with getting the new camera that we're planning on getting for this telescope. We don't have one yet, but we're going to be getting one fairly soon.
Agapios, I have some questions if you don't mind.
Yeah,
First
go
of
ahead.
all, when you capture in mono, you have color camera. Is that changeover something that is done through fire capture?
So fire capture basically ignores the color information, and then AutoStacker remaps the color information when you're stacking.
Okay.
So in essence,
AutoStacker knows the Bayer arrangement of the sensor. It knows what algorithm to use to remap, and fire capture basically is able to ignore that and just get the light information from each pixel.
Okay, that's great. The other question is, you had mentioned about you had an atmospheric dispersion adjustment thing. That's
Correct.
when you have, you know, when you feel the time is right to discuss that, could you go into that a little bit more?
Yeah.
and
Yep. Go ahead.
to go back to the debayering thing one more time, I think ultimately what's happening is when you're capturing data, you're just not having the camera or the computer do the debayering, because that speeds up acquisition. Is that
Exactly. Yes.
right?
Yes.
Or
Yes.
have you
Yes.
got some
Yes.
other
We're doing the
mathematical thing going on?
debayering when we're processing.
You're not debayering during as you're showing the video during capture.
No.
You're debayering during processing.
Exactly. Yes.
Okay, great.
So the atmospheric dispersion corrector, sorry that we can't show it to you, is a critical little device that basically cancels out the effect of atmospheric dispersion. To put it simply, atmospheric dispersion is basically the discoloration or the distortion of light as it's coming through the atmosphere. This is much more visible when your target is low on the horizon. Chris is showing it now. Can we show Chris on the call?
I think if you pin my screen there.
Let's see how we can do that. Hang on. I'm not sure I know how to do that. I'm just going to stop sharing momentarily, and maybe can you share?
Yeah, I think my camera should be pinned.
Okay, so that's your, okay, there's Chris's camera, and okay, here's the optical train. So this part here is the focuser of the telescope, and this part here is the filter wheel that we have, and this is the atmospheric dispersion corrector. Now inside this are two prisms that once you orient them in a specific way to each other and to the horizon, can cancel out the effect of atmospheric dispersion. And this works extremely well. It's a very, very cheap or relatively cheap accessory that is an absolute must-have if you want to really get the best possible resolution from your telescope. Highly, highly recommended. I have a very in-depth presentation on it, really, really in-depth. But basically, the principle behind it is because dispersion happens in sort of a parallel way, there is a way using optics to cancel it out. Let's see if I can share my screen now. Okay. Can you guys see my screen again? The live feed?
Yep.
Okay, excellent. Let's just get Jupiter back on the screen. Yeah, we seem to have, for some reason, we seem to have some lag. I'm not sure if it's the computer or the internet. It shouldn't be the internet because we've got fiber. So it's probably my computer. There we are. Okay, so as I said, the atmospheric dispersion corrector must have, absolute must have. More than happy to answer any in-depth questions over email or text. But the principle is that you get it in your optical train and you line it up in a specific way to the horizon, and then you adjust the two prisms in a specific way to each other. And there's a way that you can eyeball it if you want, but Firecapture has a really good and really accurate tool that basically uses the live feed coming from the camera to gauge the discoloration and guides you onto how to orient the two prisms so that you completely cancel out any dispersion. And I've done quite a bit of testing of this device. And what I can tell you is that it is an absolute necessity. Even if in the case of Jupiter now, Jupiter is at the zenith right now, nearly at the zenith for us, and even so, I purposely do not have the ADC adjusted properly, so that you can see the dispersion that's going to come up when we do some processing. It's definitely a must-have accessory. So speaking of processing, should we try and do a quick set?
Yeah, let's give it a shot.
All right. So we're going to be using AutoStacker to see. Let's just load up the last video. So here we have AutoStacker, and what we're going to do is we're going to trim down our file now. We don't really need all that black space. And so what's happening now is you need to remember just how video works. Video is basically lots of pictures of the same object back to back. So consider that each capture is a collection of frames. And because we live in a planet with an atmosphere, the atmosphere has turbulence, and that gives variability in the quality of the individual frames. So when we capture a 60-second video file, and each second is made up of 100 individual frames, those frames have different quality levels, and those are random. And the better the seeing you have, the less random that variability is. The worse seeing you have, the more extreme that variability is. And an easy way to visualize this is if you consider a deck of cards that are all shuffled, and you don't have any of the special cards, just the numbers. So if you go one by one through the cards, you have something like 9, 1, 4, 5, 7, 2, 8, 8, 4, 2, whatever. You have a random quality of individual frames. So what you can do with a software like AutoStacker is basically go through the file and sort your deck of cards so that you've got your 9s first, then your 8s, then your 7s, then your 6s, then your 5s, and so on and so on. So this is what we're going to do now. We're going to go through the file. We're going to analyze it. And so it's going to go and look at each one, and it's going to come up with an evaluation of the sharpness of the individual frames. And what you're getting is this graph, which is technically made up of 3 different things. You have the purple grid, that's in the background that basically signifies from left to right the beginning and the ending of the file, and from top to bottom the difference in quality of each frame. So that's your
Agapios,
first.
No, we're not
Yes.
seeing
we're
the
not
chart.
seeing what you're,
Oh, sorry. Terribly sorry. Sorry guys. How about now? There we go. So what we did is
still
we
not seeing it.
Now
No,
we're
it's
just
still
seeing.
fire capture.
still not. Oh,
Share the entire screen.
I thought I did.
There you
Is that okay?
Yeah,
Yes.
right
Yeah.
there.
Okay. Sorry about that. So all I did was I brought up my video capture, and I just adjusted the width and height so that we're ignoring the dead space and we're just concentrating on the planet. Now, I just clicked on analyze, and we got up to the point where we can see the quality graph. Now the quality graph is made up of 3 elements. The main element being the grid in the back, the purple grid, that signifies from left to right, beginning of video to ending of video. So that's second number 1 to second number 60. And top to bottom is good quality to bad quality. The second element of the graph is the wavy pattern. Now the wavy pattern is the variability of the frames as they were recorded. So the peaks and the valleys and the dips are the variability of the seeing. If we were at an extremely good tropical island, whatever, extremely good site where seeing would have been perfect, the wavy pattern would have been a line and it would have been at the top. Now, because it's wavy and because it's somewhere in the middle, this signifies that the seeing has what you would expect at a typical observing run. Now, the third element is the green curve. Now, this is the work that has been done, the shuffling that has been done from AutoStacker. So what AutoStacker has done is it's taken the deck of cards and it's sorted each frame so that all of these at the beginning are the 9s dripping down to the 8s, the 7s, the 6s, the 5s, the 4s, and so on and so on. So we are now showing the best frame, the very best individual frame. And if I scroll to the end, this is our very worst frame. Can you see the difference?
Can you go back again, do that over?
So now we're at the worst frame,
Okay.
and now we're at the best frame.
Okay.
Oh, yeah.
Yeah.
So now AutoStacker has shuffled the deck of cards in a way where we can keep only the best ones. Now, what I typically like to do is shoot at a high frame rate. So that means I end up with a lot of frames to begin with. And when I stack, I like to be strict, but not too strict, which means what? I typically try to stack about a quarter of the total number of frames. So let's say I capture 1,000 frames per file. I'm going to stack about 250. In this case, we've captured, let me see if I can read that. We've captured 7,829 frames for a 60-second file, and we're going to keep 25% of them. So the stacking is only going to concentrate to these frames, just these, the best ones, the best 25%. So I'm going to choose 25%, and I'm going to set my alignment points. Now, alignment points are little boxes that the software uses to judge features in between frames so that when it stacks them, when it combines them, it gets them perfectly right. with relation to one another. So you can play around with box size to something that is capturing quite a lot of area, so that you can tell that there's places of contrast because it's contrast based. So I'm just going to go ahead and just, that's a little too big. I'm going to just set alignment points overlapping one another where things have noticeable contrast. So I typically like to go to the north and south equatorial belts and just do a grid of boxes overlapping each other, covering different areas of the planet. And you can try and experiment with this all you like, and come up to what works for you. So I've got my boxes placed, and I'm just going to go ahead and stack. So we're now going to stack only the 18, 1900, whatever, best frames. So we're only going to be keeping those. So we're going through a stack. It really helps if you have a powerful computer, because when you've got 200 of these back to back, it can take some time. So there's our stack, and I'm going to bring up our old friend Registax, which is the software that we're going to use to sharpen the stacked image that we just created. So I'm going to open up the image that we just did, which is this one. So this image is now the result of those 18, 1900 better frames that we decided to keep and stack. So all of those frames are now embedded into this image. And we're just going to go ahead and start sharpening. Registax uses these wavelets, basically sharpening filters with different, not sizes, what's the right word I'm thinking?
Spatial frequency.
Something like that, yes. Thank you. So we're just going to start sharpening, and you're going to immediately notice the improvement. And I can tell you one thing, I really like what I'm seeing here. Wow.
That is very impressive. Look at
Oh,
swirl.
wow. Guys, this is a first for us too. This is the first time we're getting this too. Oh, look at that.
We don't seem to have much color shift, presumably because Jupiter's very close to the zenith, right?
Exactly, yes. That's actually really nice. Oh, wow. Sorry, I got really excited.
Yeah, lots of nice color in that.
Yeah, I just did a automatic balancing of the color, and let me just stretch a little bit. Well, that's not bad at all. Not bad at all.
60 seconds?
Yes, 60 seconds. Well, basically divided by 4 combined.
Yeah, we're close over here.
Yeah. So
Yeah,
yeah,
well,
that's
you're
it.
going to share this data with us, aren't you?
Of course. Of course.
Now,
and
the adjustment of the wavelets, that's just a random thing you play around with for the most part.
It started that way, but then it became something with some cohesion. Let me explain. Think of the wavelets as brushes of varying thickness. So wavelet number 1 is the finest. Wavelet number 6 is the coarsest. So let me just reset that. So if I go pushing the 6, things become bad really quickly. If I only use 1, there's barely any difference there. So what you want to do is you want to start somewhere in the middle, and then depending on the quality of the data that you're playing with, first you go with the coarse and then you go with the finer, and then with the finer, and just strike a balance between resolution and image fidelity, or realism, let's say. You don't want to come up with a pastel drawing. You want to come up with a picture, a photograph, a realistic depiction, not something that's too how do I put this?
Artificial.
Too artificial. Yeah, right. So you want to strike a balance, and only you know what that balance is for you. I like to play it safer and just stick to less sharpening if possible, because I really don't like seeing too many artifacts, or just really rough and grainy looking images. I think less is more in this case.
So,
So yeah,
Agapios, how do
yeah.
you know whether or not to use linear or dyadic, or do you adjust noise reduction in there as well?
Yes. Good question. Um, Dyadic is basically a more a finer control than linear. I don't know exactly what those two terms mean. I think there's some math involved in that,
Yeah.
which I'm terrible at. But I found that dyadic is more there's this finer control, and you can play around with the amount of sharpening, the intensity of sharpening, and you can also denoise each one of these. So what you can do is, when you're happy with the amount of sharpening you've introduced, if you have any noise coming in, you can individually apply denoising to each one of the filters, so that gives you just so much more control in letting the data come through. So it really comes down to you experimenting as much as possible. But one point I would like to make, and again, this is something that we were talking about before. You can experiment all you want. If you don't become consistent in the way you do things, then all you're going to be doing is experimenting. You need to uh, introduce methods. You need to stick to a process so that things become repeatable. When things become repeatable on your end, meaning you've collimated, you've let your telescope cool down, you're using a method in capturing, and you're using a method in processing, then the only thing that's left that's variable is the only thing that you cannot control, which is the seeing. If you don't stick to a plan, then you could be chasing your own tail when it comes to which setting to use, and which software to use, and which camera to use, and which telescope to use. That really doesn't matter. I highly want to emphasize that we need to be as consistent as possible in this game. It's the only way you can pinpoint potential mistakes, and it's the only way that you can really concentrate in improving and really getting the most out of your equipment and your time at the end of the day.
Now, do you ever turn off layers that you're not using, or you just
No, not really. What I found is, again, this comes back to being consistent. If you do start doing things with a certain way, you will find that you're always using the same wavelets in roughly the same way. So I have found that I'm almost always using, on Jupiter, for example, in average to good seeing, I'm always going from 3:1 in roughly this configuration, and I may need to use a little bit of denoising on one, but that's just what I have found that I'm doing with my equipment, seeing, and methodology, and the same will apply to you if once you've spent a lot of time under the sky with your telescope.
Thanks. I think, Bill, you had an answer for the,
Yeah, one or two things I'd add. Dyadic means that, well, each of these, layer one represents the finest detail in the image, and whether and to what extent you're trying to sharpen that. And then layer two is potentially is typically going to be double that. The dyadic thing means that layer three is going to be 4 times where it could go 1, 2, 3, 4, 5, 6. With dyadic, it goes 1, 2, 4, 8, 16, 32. So you get a bigger range in terms of the apparent size of the features that you're trying to sharpen. And as long as you're getting enough contrast between the equatorial cloud bands, for example, and other things, you don't have much reason to sharpen something that's as big as a barn. What you need to sharpen are the things that are smaller and finer that are maybe not as sharp as you'd like them to be. So.
Well, thanks for that explanation. That was brilliant.
I think you were saying the same thing, Agapios, but in not so many words.
Yeah, it's.
Well, one other point I would like to make, slightly humorous, is thank you guys for agreeing to do this in more civilized hour for us. Getting older, I've found that it's become extremely difficult for me to do this sort of thing at 3 in the morning, 4 in the morning, or whatever, as we did last time. So now it's barely after midnight for us. So we're all, we're really grateful for that. So thank you for doing this in your Saturday afternoon. I think I'm coming through much more coherent than other times.
Yeah.
Well, and actually, I think this is a great time for us anyway. The afternoon, works great. Since we don't have to make a telescope work where we are.
Yeah. So we are just gonna try and go to Mars. I think the cable is fine. Yeah. Let's try and get Mars on the finder.
So, do you think it's still worthwhile to, with Jupiter where it is right now, to try to use the APC? Is it atmosphere?
We're actually trying to. We're going to Mars, and we can show that on Mars.
Okay.
I can show you the actual process. Let's just get the telescope lined up.
It'll be more important on Mars.
Yes, absolutely.
Yeah.
Is there a way that I can hide this bar, guys? Can this one? Yes. Yes. This one? Yes. Okay. Yeah. All right. No, that's fine. I can keep that there. No, it's fine. Do you need to go further down? A bit more?
So, Agapios, I see you're wearing some winter gear there, right?
Yes.
It's cold in Cyprus, huh?
Well, we are at 4,500 feet, so.
Oh, that's right.
Yeah, actually, it's not really that cold tonight. Last time it was much colder. I think it must be something like I don't know, maybe 6 Celsius, 5 or 6 Celsius, something like that. Which for us is polar cold. But for you, it's probably Tuesday. I don't know.
Yeah, I mean, you were talking about collimating your telescope, and I'm worried about putting together my snowblower.
No. I mean, living in Cyprus, our winters are very mild. The coldest we ever got I think on the summit, which is 6,000 feet, I think we got something like -12 Celsius, which is not that bad. Down at sea level, it's almost always something like 15, 20 degrees Celsius. But the summer is brutal. The summer can be really, really brutal. I mean, especially this year. This year was, oh, I think you passed it. Yeah. Just zoomed past the screen. Let me turn it so that you can see. It went that way. This summer was something like 3 months with temperatures, daytime temperatures over 40 degrees Celsius, which was really, really brutal. Yep, there you go. Yeah, okay. I can have that now. Thank you.
Yeah, well, I think the coldest we've gotten here, we had 4 days in a row of -21 degrees Celsius.
We would all die if that happened here. All of us. Every single one of us. So, talking about the ADC, if Chris, can we do what we did before when you used your laptop to show the imaging train? Okay, so bear with us. We are going to share Chris's screen. Are you going to do that? Can need to figure out how to do it. Oh, there we are. Share. Yes, I can see you. Excellent. Okay, so let's come up to the optical train. Let's mind the cables. Okay. Should we close it? Is that better?
1 moment. There we go.
All right. Can you guys see the optical train here?
Yeah.
Okay. So the ADC is here. Now, if I could show you the other way around, let's see. Do we have enough cable to do that? Okay. Okay. That's better. So here's the ADC, and it comes with a bubble level and these two levers that basically adjust the orientation of the prisms. So the first thing we want to do is we want to make sure that the entire imaging train, when the levers are in the neutral position, which is sort of the halfway point in their travel, we want to make sure that the whole thing is leveled with that bubble level. So I'm going to do that now. There we go. And from here, we can adjust each prism independently so that we cancel out atmospheric dispersion. But we're going to keep it at neutral for now. And we're going to go back to the telescope to show you how the adjustment happens in the software. So we should stop that. And okay. Are you guys seeing my screen now?
We see Mars and fire capture.
Okay. You can see it, but I can't see it. Okay, there we are. All right. So first things first, you want to make sure that before adjusting your atmospheric dispersion corrector, your target is at the absolute center. And the reason for that is because atmospheric dispersion correctors are strictly on axis. So you want to be at the center, at the very center of your optical axis. They work beautifully on axis, but they introduce all kinds of issues, namely astigmatism, severe astigmatism at the edges of the field. But because we're shooting planets and planets are tiny, we don't really mind, as long as we get things right in the center. So what I'm going to do is I'm going to place Mars in the very, very center. and I'm going to crop in, bring this up to 100%. I'm going to disable the crosshair, and I'm going to enable the ADC tuning tool. So what that does is it's showing us these two circles, the blue and the red. What we want to accomplish is to get the two circles to overlap as best as possible. Now, what we can start doing now is, Chris, can you go and I can guide you? Go up to the dispersion corrector, and you've got two silver knobs. You can try and loosen those just slightly, and then take the one that's closer to the camera and just push it up just one notch. There's a dial on the bubble level. Just push that one up one notch, and then push the other one that's closer to the telescope, maybe 2 notches down. Okay, so that, as you may have noticed, that shut the planet out of the field of view because the prisms are shifting the optical path. So I'm going to bring the planet back up, and you may notice that dispersion has shifted slightly. So we need to do this combined. So we need to be looking at the screen and adjusting at the same time. So I'm going to come up, and can you go to the laptop, Chris? Thanks. Guys, give it up for Chris. He's being an excellent assistant.
Woo!
All right.
Guess you need a raise.
Yeah. Can you bring up the crosshair?
Yep.
Okay. Let's bring it. Oh, I got it. Okay. So I'm adjusting one of the knobs now, and I'm gonna adjust the other one.
No, you really need patience for this.
Oh yes. Tell me about it. So what you want is to get the two to overlap. And depending on the telescope, the optical configuration of the telescope, and the altitude of the target at the time of adjustment, the knobs will be in different places in relation to one another.
That's right. You got to keep updating this, don't you?
Yes, roughly, I found that you can get away with roughly 15 to 20 minutes between adjustments. But again, it depends on exactly where the planet is when you're doing your imaging. Right. Can you try changing the exposure to something a bit slower?
Hey, there's Syrtis Major.
Yes. All right. Let me just try that again.
Already you can see the features. There's the polar cap.
That's the scene. Okay, so the blue is way out. So you need to play around with this a little bit. And when you can get the two circles to overlap as close as you can get them, then that's when dispersion is reduced to its minimum.
Does
And
the ADC bottom out in terms of its adjustment ability? It seems like it's not responding.
yes, it does, and I've seen that happen when the target is really low, which is not the case right now.
Mhm.
I think right now the problem is we haven't tried to stack. Can stack more. So that should improve a little bit. Maybe it's not. There we go. Yeah, forgot to mention, you need to boost the gain as well because it's based on how it's reading color. So you need to bring up the gain where things become oversaturated. So as you can see now, it's much more stable, and you can see that the two circles are overlapping and they're not really jumping around that much. So this is adjustment corrected at this point. So what I'm going to do now is I'm going to tighten down those two knobs so that they don't shift. And I'll come back to the telescope. When we bring the exposure back to normal levels, we will be able to see.
How many frames are you using now for when you were adjusting that?
I think I took it up to. You mean the live feed or the stacking for the
For the ADC?
I
You
think I
said
took it up to 50 or something. Yeah, 50.
50.
But we were shooting at 170 per second.
Okay.
So there we go. Dispersion corrected, and with Mars we can use an even smaller region of interest, which is, there we go. And let's just go ahead and yeah, we need to focus. So let's bring up the focuser. I'm going to shift things a little bit again. There we go.
Wow, that's like a ping pong ball bouncing around.
Yeah. But look at that. So we're focusing. I think we're good there. Somewhere there. No, wait. Okay, I'll put that back. Thank you. Let's bring it back to the center. There we go. Okay. So we're going to adjust our exposure to about 50% histogram. And let's do a test run. So capturing Mars now, and Mars is currently at 12.3 arc seconds across. I think this apparition, the maximum is going to be something like 15, 16 arc seconds across at closest approach. So it has a little bit of a way to grow. But yeah, you can already see prominent features easily. Sirius Major and the north polar cap. What we're looking at there in the south, it looks like a polar cap in monochrome, but it's actually the Hellas Basin, sort of a bright valley, Mars.
Now, the reason you went up to the 300 frames per second for Mars is just because it's smaller, or is there another rationale behind that?
Because we can.
Because you can.
Yes.
Okay.
You want to go as fast as you can.
Okay.
And
And that would
because,
really be the same as
yeah,
for Jupiter. If you can go up to 300, you should
yeah,
do that.
yeah.
Okay.
I'm still waiting for the 1000 FPS camera to come up.
Okay.
When
So
that comes up, I'm there. I'm the first one. Okay, so we did one sequence, and let's bring up auto staggered, and let's get rid of this. Go to Mars. One other thing I wanted to mention. So this computer is connected to this little wonder drive that Chris actually discovered. It's a what is this? What do you call this?
It's an M.2.
I feel so old, Lou. I feel so old. It's a
NVMe enclosure with an M.2 SSD.
I don't know if you understood what that was.
M.2 NVMe.
Yeah,
Got it.
it's some kind of a really quick drive,
Oh,
extremely fast.
sure.
M.2 drive. Yeah, they are connect right to the motherboard. Crazy.
Yeah, he brought this up last time we came up, and because we needed some extra storage, and I was so impressed that I didn't let him have it. I bought it off his hands right away. It was really, 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 really quick, and it's really quick when you're processing as well. So here's our Mars capture. So we're just going to go through that and do a quick analyze. So at 300 frames per second, that 90-second file gave us nearly 30,000 individual frames, just for perspective.
Wow.
Yeah, so this means that if I wanted to stack, say, 10%, that's still 3,000 frames. So that's why you want as fast as possible.
You won't
So
need much noise reduction because
if
the
any,
will be super high.
if any.
But if you go to the fastest possible frame speed, doesn't that cut the amount of light you're collecting in each frame and increase the noise in each individual frame?
Yes, but you need to factor in the resolution that's coming in because of the seeing and your telescope as well.
Mm-hmm.
And when you're stacking many thousands of frames, you don't have to worry about loss of signal because the signal to noise is high.
Yeah. I have a question too about the alignment points. Normally
Yes.
I would think of an alignment point as some feature that's readily recognizable and relatively high contrast in both dimensions, X and Y. And with auto stacker, you seem to pick alignment points that are just everywhere.
Yes and no.
No. Okay.
You pick the center of the alignment point to fall on a feature that has high discernibility, high contrast.
So a
So if you notice,
boundary.
if you notice the red dots are falling on the boundaries between dark areas and light areas, or snowy areas and dusty areas.
Okay.
But overall, you want all of your alignment points to overlap to one another fairly generously, because alignment points are used to recombine the final stack from all of those many thousands of individual frames. So let's.
Okay.
That's why you use such a large box.
If you've got the resolution, you can try smaller. But I've found that if you use really small alignment points, then you start to see artifacts coming in,
I see.
grid patterns and stuff that isn't really there. So you need to strike a balance again.
Well, that came out really nice so far.
Yeah, that's not bad either. Let's try and
Polar
enlarge
cap.
that.
Impressive.
Okay, yeah. Not excellent, but not terrible. We can see Syrtis Major, we can see the Hellas Basin, we can see the polar cap, a good amount of detail. Now I know that under better conditions and with more carefully tuned collimation, the telescope can do much, much more. It's just a matter of hitting the right conditions, the best possible conditions. But all you have to do is just click reset and see what the stack looks like before sharpening, and then just play with the wavelets to really pull out the detail there, and that really goes to show the incredible power of all this software, all this all this freeware, by the way.
Yeah,
Yes,
isn't that amazing?
it's great. One thing I noticed, and maybe this is just on my monitor or something, but if you look really closely at the image down the left side, the finished image,
Yes.
down the left side, there was definitely a red fringe, and down the right side, there was a blue fringe, which makes me wonder if the ADC is actually adjusted as well as we had thought we got it. Do you agree? Do you see a red fringe on the left and a blue on the right?
Yes, you're right. So we didn't really tune it to the best possible. Yeah, you're right. There's definitely red this way.
Yeah, the blue disappears better in the shadow on the right, but I think there's
Yeah.
still a little bit of a hint of blue there.
Yeah, I'm not surprised by that, but at all. You really need to spend the time to get it as perfect as you can. But to be honest, it never really goes away completely. For
Right,
for
and
for a
and I was
variety of reasons. For a variety of reasons. But all you have to do is purposely misalign the atmospheric dispersion corrector so that you can see what the image would look like without the contribution coming from it. And when things work right, I can tell you that I've seen incredible improvement from the resolution coming out of a telescope
right.
with a dispersion corrector.
And if it has done the vast majority of the correction, you still have the possibility of using the RGB align to try to
Yes,
squeeze out the last
yes,
little bit.
and you can also do that during the stacking process in AutoStacker as well. AutoStacker has its own RGB displacement tool that can help to line up the channels of each individual frame before combining them to a stack. And then again, you can do it with Registacks with the RGB alignment tool. And ultimately, if all that fails, you can cheat in Photoshop if you want.
So, Agapios,
Yeah.
what I'd like to talk about now, what your telescope is going to look, this observatory telescope is going to look like when you're done ending the camera. So, do you plan on using a 4x, 3x, 5x teleview, 2x? What's the pixel pitch you plan on using? How big of a sensor? What do you guys, what's your budget and what do you have in mind there?
So for Planetary, I don't think we're going to change anything. The maybe change the amplification factor, so maybe change the Barlow lens, but the current camera is actually really good. For deep sky viewing, deep sky imaging, we are contemplating, probably we've decided that we're going to go with the new C3 from Moravian. I don't remember which sensor that is. I think it's the 455 sensor. That's going to be a really good upgrade for this telescope. So that's going to feature filter wheel, guiding system, off-axis guiding, a full set of LRGB and narrowband filters. I don't remember exactly what pixel size that has, but we can look it up.
Is it the C3?
The C3, the Pro,
the full
one with
frame?
yeah.
Wow, that's $6,700.
Something like that, yeah.
It's got a
Yeah, so that's 3.4 micron pixels, 9.5 by 6.3 thousand pixels. Yeah, the Sony 455. We've done some looking around, and it looks like it's the best pair for the telescope. So I think that should be coming soon.
Okay, and the camera that you're using now is your own personal camera.
Yeah.
So for planetary imaging, you plan on using something like that, or?
Well, we also have a couple of what's the sensor on those? The 294 MCs planned, primarily for using them with the solar telescope. We've got a 100 millimeter H alpha telescope in the other observing room. But for serious planetary work, it's going to be this camera, the one that we have on now.
That's your camera.
Yeah. At the moment, well, as long as they let me do it, it's going to be my camera. So
right.
Are you getting clouds?
Yeah. There's some clouds coming in.
So you haven't decided what F ratio you're going to be shooting, and what works the best with the pixel size for.
Well, typically you want to be at five times the pixel size, typically. And that would mean 3.75 times 5. That would mean something like f16, and we're now at f12 something. So we need just a tiny bit more amplification factor from a Barlow lens, which actually, if I had thought about it, I would have brought it up with me, because I've got quite a few that we could try. But yeah, that's the easiest thing, that we can just change the Barlow on the setup.
I mean, I think that it would be sufficient for Jupiter, but for a small planet like Mars, you could see some pixelation, for maybe undersampling.
Yeah.
I was wondering if it would be a way around that. But if the primary mission of this telescope is deep sky, then it, that makes sense to use the other one. All right, there's just a couple of questions that I had. First of all, thank you for doing this for us. I've never seen such a large scope under such amazing skies. I mean, what would you predict the seeing is by looking at the data we collected today? Like Jupiter was pretty impressive.
I don't want to put a number on it. I'm just going to say very usable. Very usable.
Usable.
Yes.
I mean,
I've seen much better seeing. Not from this telescope and this site, but other sites on the island. I've seen much better. But ask me again in a year, after I have done a good number of observations with this telescope, and then I could probably give you numbers. But I'm going to stick to very usable.
Right. So Mars it doesn't, when is Mars transit? Next month?
I think it's early January.
Yes.
All right, so we're expecting some images, I guess, then. And then the next planet should be Venus is kind of boring, but the next planet should be Saturn. And then that's September, I think.
It was back in
We
September.
actually did with Chris. We actually did an attempt to shoot Titan's shadow transit, but Saturn was something like 15 degrees at the time when we shot that, and all we got was a blur. Well, you can make out the shadow, but nothing compared to the kind of conditions that we got now tonight. Um, but I'm very, very hopeful that given time, we can put out some really interesting shots with this telescope from this location.
Yeah, Saturn will be, I guess, edge on next time around. So we'll just see the very thin line.
Yeah.
No Cassini division.
Well, we're getting some pretty heavy clouds now.
Right.
Yeah.
Well, Agapios, thank you for this wonderful presentation.
My pleasure, guys. And just I wanted to emphasize that as you know, if you don't know, I'm always available and very keen on corresponding with people who enjoy this sort of thing. So please feel free to reach out on email or social media or whatever, however you want. I'm online most of the time. I barely sleep. So feel free to reach out with any comments or questions or anything else you would want. I highly enjoy doing this sort of thing, and I really enjoy talking with people who enjoy the same thing. So feel
That
free.
is definitely obvious. But before you go, I was wondering if Tom Nolasco, if he's still here, if he wouldn't mind sharing his video of Jupiter.
I am here.
Yeah, hold on, Tom. Let me make John. Can you make Tom co-host, please?
Done. You got it.
All right. And then also Agapios. We want you. Can anybody tell Agapios what it takes to log into the groups.io so he could be privy to that information? Does anybody know how that works?
Oh, that is beautiful, Tom.
Wow.
Yeah, that is spectacular. Nice.
There's the storms right there.
Mhm.
That's the southern the disturbance. That's Io going across.
Wow. That's great, Tom.
Thanks.
For this,
Really well done. Really well done.
I got
Is
this
this with your Newtonian?
Yeah, it's Newtonian. It's the 10-inch Newtonian.
10-inch
And what
Newtonian,
camera?
yeah.
This is a 462.
Hmm.
It's
Very
really
nice,
replaced by the 662, which has basically the same specs, except that it has a deeper well, the 662. And it's a lot cheaper. The 662 was on sale for, I think, under 140.
Wow.
Unbelievable. Right now, Black Friday sale. But here's just a single shot of the SEB storm. You kind of can see it there.
Wow.
That is really nice, Tom. Really
Nice.
well done. I mean, you can really make out the altitude difference. Bright clouds are high altitude clouds. Dark clouds are low altitude clouds on Jupiter, and you can really see that on your images. The processing is just right to really show this depth really well. You've nailed it when it comes to
Thank you.
That's really good. That's really well done. Really well done.
So where was your site? Where did you get the data from?
Just in my backyard.
Okay. Pennsylvania, New Jersey.
Pennsylvania, just the northeast suburb of Philly.
Okay.
Yeah.
Wow,
Underneath the
guys, good
jets.
seeing that night.
It was actually just kind of average seeing, but I did
Yeah.
a lot of things. You watch the video, you can see the scene go in and out. Actually, you know, you can see it because I'm just shooting frame after frame and putting together like 50 some odd frames. And you can see it fade and come back and fade and come back, you know.
You know, you're giving me a great pass now, because one of the things that I very often talk about is that the great thing with the cameras that we have available now and the ability to shoot at really high frame rates is that we are able to harvest good seeing where we're unable to perceive it. So when you're looking at the live feed, you're looking at more than 100 individual frames every second. And I don't think that our brain can actually process that accurately. So with this kind of imaging, you're able to harvest conditions that you're unaware of. You're really not seeing it. Can we? Oh, so Chris just pulled up the specs. We can do 30 to 60 frames. Our brain can do 30 to 60.
Okay.
And we can shoot at hundreds.
Yeah,
So
this was
that explains why when you're looking at the screen, your perception is that it's only so and so, when in reality there's much better quality data in there that you're just not able to see. So
yeah, from your
this is
past
where,
talk, you talked about
yeah,
frame rates. So this is like a 142 frame rate, frames
yeah,
per second, because of
142 individual frames every
yeah.
second. How can you possibly keep up with that?
The
So my whole point is getting the luck out of the lucky imaging. Just do whatever you can so that you can harvest conditions when they happen overhead, and you've done that, and that's just brilliant. That's really, really well done.
Thanks.
what do movie editors what is it, 24 frames a second is what the human eye can perceive. And you've gotten a fact like what, 5 times more than that? That's just insanity. But
The trickiest part is focusing because the scene's going in and out, and you're kind of, you know,
Yeah, yeah.
you're trying to
Well,
adjust
if
it.
you
And
if you can get the focus right, then just, I don't know, just wait for it.
yeah,
Wait until things look better.
yeah.
I don't know if this is me, Tom, maybe my brain's playing tricks on me, but if you notice the middle band, right on where the shadow is,
Yeah.
that weather pattern looks like it's moving to the right a little bit, and the one below it, it looks like it's moving slightly to the left, counterclockwise versus clockwise. There's a very minuscule, I mean,
Well, they're actually rotating. I mean, the bottom ones rotate slower, right? It's a gas.
Yeah,
So,
you can see that. You
yeah.
can see that.
yeah, I mean, that's the first time I was able to perceive that in any movie. But I'm partial to your solar images, so I would love to see more. Yeah, you got to go visit Agapios over there, Tom.
I would love to.
You're more than welcome to, Tom.
Anyway,
Tom, do you know, or does anybody know how to instruct Agapios how to sign up to the groups.io chat?
I dropped a link in the group chat there, but
Can you see
So
that?
this is like a chat group.
yeah, I think if you created an account, you could set it up to get a daily digest, like an email once a day of all the stuff. It's like an internal chat
Right,
within, like a user group type thing.
Yeah, like Tom puts all his images there. If we're going out to image, we'll message each other. But a lot of us put our images there, and I put the note about this meeting in there.
Right.
Not everything may interest you, but you'll definitely see the most important things in the club, because I don't want you to miss some important events, and I'm sure people would love to hear your input.
Yeah, absolutely. No. I'm definitely gonna look into that. I've just been so incredibly busy beyond belief, and it seems that every passing month it's just getting busier and busier and busier. But yeah, I really don't want to be left out. I want to do whatever I can to stay relevant. So yeah, definitely going to be looking into that.
Yeah, Agapios, we appreciate it. I guess we'll see you again next year, but you let us know if anything is new has popped up. We communicate all
Well,
the time.
the next year is next month, so you never know. So
Well,
what I'm gonna do is I'm gonna put all the data together in a drive folder. I'm gonna send you a link to that so you can download what we took today from the half-meter telescope, and you can have your own attempt at processing some of it.
there you
And
go.
I would love to see results. So
See,
feel free
How
to
many
shoot
gigabytes is
some.
that going to be? It seemed like you were acquiring data for quite a long time there.
Are you ready for this?
Go ahead, shoot. How many?
Let's see.
that would be the
So,
place for the groups.io chat if you put a link
so,
on.
so Jupiter tonight is 334.
Gigabytes?
It's your gigabytes.
Yes.
Uh,
And
yeah, I'm
Mars,
not
well, we
asking a
only
lot.
took one shot of Mars, so that's only 4 gigabytes or
Yeah.
something.
If you can, I would think it'd be great for people if you could pick, 2 or 3 of the sequences that were particularly good.
Yeah.
Because
But
that's a lot
I'm
of
gonna
data.
send you what I'm gonna do is I'm gonna stack all of them, and I'm gonna send you the stacks, and I'm gonna include maybe 1 or 2 of the best video files, so you can have a more comprehensive image of what's going on. So I would love to see results. So please do have a go and send me your results.
Yeah, I'm looking forward to
Cool.
processing them.
Yeah, sounds like fun.
Very nice.
All
Thanks
right, guys.
again.
Yes,
Thank
thank you.
you.
Agapios and Troodos.
Thanks for your
It
time.
is
That was
1 a.m.
wonderful.
Thank
for
you
us.
again.
Thank you for having us. It's always a pleasure. Really great time. Thanks, Chris, for all the help.
Thank you.
We are going to make our way down the mountain now and get some sleep. So enjoy the rest of the weekend, and we'll talk to you soon.
Yep.
Hey,
Thank you.
take care. Thanks again.
Thanks, guys. Bye-bye.
Bye.
Bye.
Bye.